I'm scarcity.
I don't buy it.
Actually, it's not, it's not the already on, that's the main. Unlimited ones, it's unlimited. That's just, I learned that. In the coffee shop.
Okay,
What is in that one? Actually, it's that.
so just kind of giving heads up for what's happening with the rest of the week. We're going to do related rates today. But there's no homework tonight. I'm gonna be checking pages 9 through 12 on Friday. So today's related rates, tomorrow is just fall semester theorems like EBT, mean value theorem, roles. And then on Friday, curve sketching, derivative graph, particle motion. And so I'll be checking page 9 through 12 on Friday. And then Tuesday after we get back from break, I'll check pages 13 through 16. So nothing due on the Monday after spring break. But I will send out a reminder like the Sunday before we get back to school that I'm gonna be checking homework on Monday. Oh, sorry, Tuesday. Now, after we get back from break, I have packet 3, which you haven't given to you yet. We're just going to focus on the other kind of like the major. What I like about that FRQ, that quiz that we just took, is it kind of hit a lot of a wide range of topics that we need to know. So let's get that out of the way. And then the other of the two big topics after that are Riemann sums and differential equations. So we're going to spend a few days on that after we get back from break. So I'm a packet 3, you'll work through those packet, and I'm also going to kind of bring in some previous FRQs that we've done. And then you'll have no quiz the week after we get back from break. But then after that week, Tuesday, will be another FRQ quiz, but just over Riemann sums and differential equations. And then after that, we're going to start preparing for the multiple choice portion. Wednesday, Thursday, Friday, we'll review. And then Monday and Thursday will be the quizzes. The reason why it's kind of like on a weird day, I'm not having it back to back, is because these are mainly going to be 30-minute class periods because of EOCs. And the Monday and Thursday are the longer days. I think Tuesday and Friday are even shorter than that. So it'll be 8 multiple choice questions on Monday, but just over fall semester topics. And then we'll spend 2 days going through the integral topics. And then Thursday, you'll take your integral topics quiz. That'll also be 8 multiple choice. And then that will go in as a test grade. So this will be 25 points, and then your homework up to that point, the homework packet will be 50 points. So there'll be a 100-point test grade. Okay. And then no formula sheets on this multiple choice test. Okay. So that's the last thing before May. And then when we get to May, I'm going to be going over the FRQ packet that you have in front of you. So what you picked up now is not due until the end of the school year. Okay. And this is also crazy week because this is when AP exams start. So students will be in and out of the classroom, but I'll be spending time going through various FRQ problems from the packet. And then yours is going to be turning this in before the end of the school year. Right. But the reason why I want to give this to you now is because in case you wanted to kind of chip away at it. Okay. Even though it's not due at the end of the school year, my preference is that you can get the packet done before the AP exam so that you would have seen everything before the AP exam. But I'm not going to require it because everyone, has a lot of things on their plate. So, but I figure if I give it to you early, then that gives you the option of working through it and kind of a piece at a time if you want to. There's also, and so this will be worth a quiz grade. Okay, so if you just if you complete it and do all your work, and you also have the solution key in front of you, then that'll be worth a quiz grade. And then there's also another take home, the multiple choice tests, which I will give you after spring break. But I figured the FRQs take a little bit longer, so I wanted to kind of give you a head start in case you want to do that. So here are the remaining grades that's going into the grade book. We just took FRQ quiz 1. Okay. FRQ quiz 2 is the week after spring break. Multiple choice tests will be after that. And then assessments 4 and 5, these are both quiz grades, and these will be just whenever you guys finish it, I will take it and enter it to the grade book. Any questions? Just want to show you real quick. On my website, under spring break, I recorded the videos for these FRQs. So, I mean, you guys have the solution key in front of you, but if you wanted to see me work through the problems, you can just click on those links. So that's available to you in case that could be helpful. So. So again, this what you have in front of you is assessment 4, and then I'll give you the assessment 5 take home sometime after spring break. Right, so these are not due until end of the school year. Ideally, I would like for you to finish both of these before you see the AP exam, but that's just my preference, but I'm not going to require it because you guys will, you guys have to manage your own schedule and everything, so. Any questions? Everything's clear in terms of what's coming up, what the grades are, and what's expected. Okay, so if there's no questions, let's go to your previous packet. And our next topic is related rates. And this is one of those topics, kind of like limits. We just haven't seen this in a while, right? We did not touch this after, as soon as we got done with this unit, we kind of did not revisit it until now. Okay, so related rates, these are all kind of word problems, and they'll all have time involved. So you're always going to see the word when, right? So there's always going to be time involved with these related rates problems. So these problems are where we relate the rate of change of a dependent variable with the rate of change of an independent variable. And that independent variable is always going to be time. Okay, so the first step is we want to identify the equation that we're working with. Is it the Pythagorean theorem? Is it a volume of a shape? Is it a surface area of a shape? Is it a trig equation? If it's a trig equation, we'll look at that specific case. We didn't cover that until the trig unit at the end of the year. And also involving similar triangles like cones and shadow problems. So after we identify the equation, then we find the derivative of each variable with respect to time. So kind of like implicit, but instead of dy over dx is now dy over dt. So everything is over time. So every variable is now getting impacted by time. So as soon as we find the derivative for one variable, we're going to attach a d over dt. So it could be x dt, could be dv dt, could be theta dt, just depending on what variable you're working with. And then once we have our messy variable equation in front of us, then we're reading the problem to see, okay, where do the pieces fit and what variable am I solving for? Okay, so the classic problem that we started at the beginning of the unit was the Pythagorean theorem problem, okay? So number 1, it says 15-foot ladder is sliding down the building at a constant rate of 2 feet per minute. How fast is the base of the ladder moving away from the ladder? Away from building when the base of the ladder is 9 feet from the building. So we can first start off by drawing a triangle. And then the ladder represents the hypotenuse of the triangle. Okay, so ladder is being pulled away from the wall. We know this is Pythagorean theorem problem because everything that we're dealing with is in relation to the side length of this triangle that we're seeing. So we know we can start off with x squared plus y squared equals z squared. We know we have to find the derivative, and every derivative is going to produce its own time variable or time derivative. So x squared becomes what? Yeah, 2x times dx dt. Yeah, every variable gets its own d over dt. So the calculus is done. The rest of it is just trying to figure out where all the pieces go. Okay, so let's gather some information here. X, Y, and Z represents the length of each of those sides. Dx dt represents how fast this length is changing because of the way that the ladder is sliding. Dy dt represents how fast this height of this triangle is changing. And dz dt represents how fast the hypotenuse is changing, how fast that length is changing over time. Now, what do you expect out of dx dt? Positive or negative? It's going left, but what's happening to this length? It's getting larger, right? So the reason that I drew this triangle this way is because I want us to just keep reminding ourselves that the direction doesn't matter, right? We really want to look at what's happening to that value over time. So we expect this length to grow, so we want dx dt to be positive. We expect it to be positive. What do you expect dy dt to become? Negative, because that length is getting smaller, right? It's getting shorter, yeah. Be the same thing. It'll be the same thing, right? But the reason I drew it this way was because I don't want students to associate left with negative, right? Which is not true, right? Because it really depends on what's happening to your length. Left and right doesn't really mean much. Okay. Okay, so I'm going to list out all the variables that's in play here. Okay, 15-foot ladder, where does that go? Z, right? That's the height, that's the hypotenuse length. The ladder is sliding down a building at a constant rate of 2 feet per minute. So what can we assign this to? dy dt. And what any adjustment we have to make? Negative. Okay. How fast is the base of the ladder moving away from the building? What are we looking for? Dx dt. Right, so I can put a question mark there. That's my unknown. When the base of the ladder is 9 feet from the building. X. Okay. So we want to start putting information into the equation, but there's still some missing pieces that we have to resolve. So y represents the height of this triangle at this moment in time. So what can we do to find this height? Pythagorean theorem, right? We have x and y, or x and z, we can plug in and solve for y. So a squared plus b squared equals c squared. Pythagorean theorem. This is also a variation of a 3, 4, 5 right triangle. So ends up being 12. Right? But you can use your calculator. It will still give you 12 there. dz dt, what does this mean? What does this variable mean? Rate of change of the length of the ladder. Is this ladder changing its length at all? It's going to be 15 feet at the beginning of the problem. It's going to be 15 feet at the end of the problem. So dz dt is what? 0, right? It doesn't change. Right? Over time, it's still going to remain the same length. Okay, so now we just insert into our derivative equation, and we're just trying to solve for dx dt. Okay, so use your calculator, work your way through. And what unit of measure do you expect dx dt to be? Feet per minute, and algebraically, when everything is said and done, you should be getting what type of value? Positive or negative? yeah, we should be getting a positive value. Okay, so that's a way to double check ourselves too. Okay, algebraically, I was able to work this through and I got 8/3, so B per mil. And also, something that we can do, because right now we kind of visualize what's going on. That's how we know whether to make something positive or negative. But we can also tell and decide whether a rate is positive or negative based off some keywords. So if something says, the volume is decreasing, or the length is increasing, we know, okay, those keywords are indicating what signs to make the rate. Any questions for one? All right, number 2, a beach ball, which is a sphere, in a shape of a sphere, is deflating at a constant rate of 10 cubic centimeters per second. When the volume of the ball is 256 pi over 3 cubic centimeters, what is the rate of change of the surface area? Okay, so we're working with 2 equations. We know we're going to be involving derivatives for both. And these are formulas that will be provided for you on the exam. So they will, any geometric shapes they will give you. Okay. Okay, I like to just go ahead and get my derivative out of the way. That way I can I'm done with the calculus and then I can work on filling in the pieces of this puzzle. Okay, so I have V equals 4/3 pi r cubed. Let's go ahead and get the calculus out of the way. So V becomes what? dB dt. Now 4/3 pi is just a coefficient, right? There's no need for product rule. So 4/3 pi is going to stay. R cubed is going to turn into what? 3r squared times dr dt. Okay, let me just clean this up a bit. 3's cancel out. I get 4 pi r squared dr dt. Okay, so we have 2 equations in front of us, V and dV dt. Just depending on what the problem gives us, we may have to kind of use the equations accordingly and find a piece of information one at a time. Okay, next is surface area. We know we have to involve this somehow. Okay, let's go ahead and get the derivative out of the way. S becomes ds dt. 4 pi stays. R squared becomes 2r dr dt. Now, if you just skip this step and just went directly from 2 to 8 pi, that's fine as well. I just want to kind of break the steps down in case you need to see it. Okay, so we have 4 equations at our disposal. We may not use all of them, but we want to just understand that, if we're looking for something to use, these are our four choices and we may use them at different times depending on what information we need at a certain time. But let's just gather the givens in the problem here. A beach ball is deflating at a constant rate of 10 cubic centimeters per second. Okay. What variable is this going to refer to? dVdt. So you see cubic centimeters, that's a hint. You know it's volume related. Per second, there's a time component. So volume and time, that's dVdt. Any adjustment that needs to be made with dVdt? Because, yeah, it's deflating, right? So it's indicating that there's a rate of change, the negative rate of change. When the volume of the ball is 256 pi over 3, so what variable is that? V, so that's a moment, that's just a moment of time, 256 pi over 3. Cubic centimeters, so that's, yeah. What is the rate of change of the surface area? ds dt. Yeah. So it's kind of like a puzzle because we're not going to be able to just use one equation to get to the answer. We're going to have to kind of piece things together. So let me highlight ultimately what we're trying to do here. We're trying to find ds dt. But in order to get ds dt, I need r and dr dt. I don't have r yet. I don't have dr dt yet. But can the v and dv dt help me get to the variable that I need at the end? How can the v help us out? I can use the volume equation and I can ultimately use this to help me find which variable. R. So this is the key to help me get to the R variable that I'm going to need at the end. Okay. I don't have dr dt, but how can dv dt help me out? Yeah, I can put into my dv dt equation. Hopefully I would have R already. And then if I can use dv dt and R, I can solve for dr dt. And if I can find that piece of the puzzle, then I can get to what I ultimately need to get to ds dt. Does that make sense? Okay, so let's use V first, because I think finding R is important. If we get to R, then that's going to be a piece that we need for dv dt. I can divide both sides by pi, divide both sides by 1/3. I can just get the 3 and the pi to all go away. Okay, divide both sides by 4. Take the cube root. Okay, so that's I'm making some progress here. I have the R variable that I need. Now I can use the dVdt to help me get to dRdt. Okay, so dVdt is -10. 4 pi r squared. I just found r, so that's going to come in handy. Okay, divide both sides by 64 pi. Now, something you gotta be careful here is that the pi is in the denominator, so it needs to stay in the denominator. So even after you reduce your fraction, don't just let that pi float to the top. Okay, it's gonna stay in that denominator even after you reduce that down to 64. Okay, so now we have everything that we need. We can now find dsdt because we have r that we just found, we have dRdt that we just found. I'm gonna steal some space up here. A times 4 is 32. 32 pi over 32 pi cancels out. I'm just left with -5. Now, what's the unit of measure for surface area here, or dsdt? Surface area is centimeters squared, because I focus on that word area, right? Area is a two-dimensional unit, but there's a time component, so per second, yeah. Okay, there's our answer. Okay, number 3. Cone problems are the ones that are the most time intensive because it's just a lot of moving parts here. So water is poured into a conical container at the rate of 10 cubic centimeters per second. The cone points directly down and it has a height of 30 centimeters and a base radius of 10. How fast is the water level rising when the water is 4 centimeters deep? Okay, so the reason why this takes a long time is because we have to deal with similar triangles in order to get that relationship between R and H. We need to either get R in terms of H or H in terms of R because there's too many variables and not enough information. But we do have a nice connection between our two variables here. So here's my cone. It says height of 30 centimeters. Base radius of 10. Sometimes they give you the diameter, so just be careful. You want to just make the proper adjustment. So if I were to just look at this one little piece here, I can see a triangle within a triangle because there's going to be a water level that's going to, the water inside the cone is going to create its own cone shape. Okay, it's going to kind of, but if we just focus on the fact that there's a triangle within a triangle, let's see if we can find the dimensions of these here. So we know that the radius of the water level is going to be changing over time. So we need to leave that as an R, right? As water is being poured in, that R is going to get wider and wider. But we know that the height is not going to change. So that will represent the dimension of your big triangle. But the height is changing. So I'll let that the small cone represent the height of the water level.
And then 10 is the 10 and 30 represent the container. Okay, so we're going to set up a ratio here, proportions here. So radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. So let's multiply here. Now, ultimately, everything that I'm looking for is, it says, how fast is the water level rising? What am I looking for? DH, yeah, DHDT, and when the water level is 4 feet deep. So you know that everything that's given to you is in terms of H, and that you want your equation in terms of H. I mean, we can do our equation in terms of R, but it's just faster if we can just get to the H faster. So what we want to do is we want our volume equation to be in terms of just H. So I want to find a way to get R to be replaced. I want to solve for R. So divide both sides by 30. Okay, so this is my substitution tool that I'm going to use to get my volume equation in the proper, easier variable to work with. I'm going to make my substitutions. I'm going to replace my R with H over 3. That way my right side is just in terms of H. Now this is all algebraic steps here, nothing calculus yet. We got to get this volume equation down to a nice clean form before we do derivative. And if, when we do derivative, we don't want to do any messy rules. We don't want to do chain or quotient or product rule. We just want a nice clean power rule to work with. Okay, so we don't want to do our derivative until we get our equation nice and clean. Otherwise, it just feels, it's too much work. I mean, we could do product and chain rule, but why do that if we can just do power rule? Now, I want to put my variables together, put my coefficient together. So I like to push my coefficient out in front of my variable. So my volume is pi over 27. And I like to put the H out in front. Okay, you don't have to. It just feels cleaner if I don't have to deal with the fraction underneath my variable. So pi over 27 times H cubed. If that makes sense. Here's the hardest part. The hardest part is to get to this point, because after this, the derivative should feel easier and the substitution should feel easier. But after this point, it does. There's a lot of algebraic messiness we have to kind of wade through. Okay, let's find the derivative. B becomes coefficient stays, right? So like a number in front of a variable, it's not going to go anywhere. H cubed, we need to find the derivative there. H cubed becomes 3h squared times dHdt. Good. Okay, so now the calculus is done. Now you're just putting information in. Okay, we gotta be careful with this 4 centimeters deep. I think sometimes students see this and see, oh, that's my H value, and they want to insert that 4 at the beginning of the problem. Okay, we want to hold on to our variables until the very, very end. And then this 4 centimeters, we only use this 4 centimeters at the very end. So now that 4 can insert itself in for H. dV dt is 10. And then we can now solve for H. Sorry, solve for dH dt. Water is being poured into the tank. So that's why we want dV dt to be positive, because that volume is going to be growing over time. Okay, clean this up a little bit. Dividing by 16 pi over 9 is the same thing as multiplying by the reciprocal on the other side. So 10 times 9 over 16 pi becomes 90 over 16 pi. Notice that your pi is staying in the denominator this entire time. It can reduce a little bit, use your calculator, it ends up being 45 over 8 pi. Okay, any questions? Okay, we didn't finish with there's also trig related related rates. So I want to do that tomorrow as well as cylinders. So cylinders look a lot like cones in terms of the equation, but it's a lot easier. So we don't want to mix steps between cones and cylinder. No homework tonight, but I'll be checking pages 9 through 12 on Friday. I just cleaned up as I went along. 3 over 27 is 1 over 9, so that's good. I didn't have to do that. I just figured, okay, if I can kind of tidy up as I go along, that's why. Okay, come and get your phones. So, yeah, so.
I know I was.
So f of negative 3 is my final position, right? So I'm gonna insert negative 3 in for my, okay, my A value is negative 2, because that's what gives. Okay, so my final position, I just wrote that as a way of saying, that's what I'm looking for. That's the location I'm looking for. That's my.
Right, so.
Right, but this is the f prime, so we can't find the y value by looking at this graph. This is the f prime.
No, I got that. I'm just saying when I do. Or is that just?
Yeah. Right. Don't think A and B as X and Y. Think of A and B as your lower and upper bound.
Okay,
I use A and B because of like, let's see, other one.
okay.
So this is your final, that's those, yeah, everything that you see are X values. The B and A are both X values.
Right, okay.
So f of negative 3, I want to find my location at negative 3, so I need to first start at negative 2, and then figure out how much progress I made in that.
Are you starting at -2 because it's. That's your.
I started at negative 2 because that's what's given to me.
Okay.
That's what's given to me. So maybe you can think of it in this form. So let's say I had a graph here. Let's say this is 1, and this is 3, and this is special. So let's say I gave you x of 1, which was, imagine you're driving on the road, and let's say it's at x of 1 is a mile marker. So mile marker, let's say you're a mile marker 5. Okay, and this is your velocity function. Okay, so let's say between the first and third minute, you travel 2 miles forward.
and then you went backwards, you went backwards 3 miles. So asking Caitlin, how much progress did you make? Well, at X of 5. That's what I'm looking for. I'm starting at mile marker 5. But then from 1 to 5.
Yeah.
X of 1 is mile marker 5. And then how much progress did I make? I went 2 miles forward and I went 3 miles backward. So that's gonna give me a net gain of 1.
Okay.
So that means X of 5, where are gonna be 5 minutes into this car ride? You're gonna be on mile marker 4 because from mile marker 5, you're going 2 to the right, 3 to the left. So we're kind of just taking where we are and we're kind of just figuring out our progress over that time period. Have a great day, guys. See you tomorrow.
Oh, yeah. It's been great. I appreciate that. So I'm becoming a new kid, so. Thank you for. Battle. Yeah. I think I did. Creator. Yeah, that's what he said. He said he's good for the audience.